Welcome to The Explainer. Today, we're going to bridge the gap between human biology and computer science to figure out exactly how machines are taught to see color. We take our vision for granted all the time, but the mathematical and biological gymnastics required to capture, process, and analyze just a single colored pixel, it's absolutely staggering. Let's get into it. Here is our roadmap for today. We'll start with the biology of color, move right into full versus pseudo color processing, then decipher color models, look at converting RGB to HSI, and wrap it all up with some real-world applications. Starting off with Section 1, the biology of color. To really wrap our heads around digital sight, we have to start with human anatomy, mainly because computer vision is basically just one big attempt to replicate how we physically perceive light. Think about what happens when you pass white light through an optical prism. It fractures into the visible spectrum, the colors we see every single day. Out of the massive, chaotic electromagnetic spectrum out there, this tiny, narrow band is literally the only part our biological hardware can naturally detect. And speaking of that biological hardware, let's talk about the 6 to 7 million cones in the human eye. These are the photoreceptors that actually let us see color. Check out this breakdown. About 65% of them are dedicated to red, 33% to green, and a tiny 2% to blue. But, and here is the crazy twist, even though those blue cones are the vast minority, they're actually the most highly sensitive to light out of the whole bunch. So how do these sensors actually react? Well, they absorb light at very specific wavelengths. The blue cones peak right around 445 nanometers. The green ones hit their stride at 535, and the red cones peak at 575. It's the overlap, that beautiful blending of absorption across these three sensors, that lets us distinguish millions of unique shades. And crucially, this exact three-color biological model is the foundation that digital cameras are trying to mimic. Moving right along to Section 2, full versus pseudo-color processing. Okay, once a sensor actually captures that light, how does a computer process it? We basically have two main paths here, full color and pseudo-color processing. Full color processing is pretty straightforward. It works directly with data from full-color sensors, like the camera on your phone, typically using a 24-bit representation. That's 8 bits each for the red, green, and blue channels. Pseudo-color processing, though, that's like giving a machine X-ray vision. It takes a grayscale image where no true color exists and assigns false colors to different intensity levels. It's a total game changer for highlighting hidden details, like temperature spikes on a weather map that our eyes would totally miss in plain black and white. All right, Section 3, deciphering color models. Having the data is great, but we need to organize it mathematically. Hardware like screens and sensors rely on the additive color model, good old RGB. When you mix red, green, and blue light together at full intensity, boom, you get pure white light. On the flip side, we have the subtractive model, cyan, magenta, and yellow, or CMY. This is what your printer uses. Since physical pigments absorb or subtract light, mixing them all together gives you black. But here's the rub. Humans just don't describe the world in RGB percentages. If a photo looks dull, you don't say, hey, crank up the green by 12%. You say, make it brighter. That's why we use the HSI model, hue, saturation, and intensity. Hue is the dominant wavelength, the actual color we see, like red or blue. Saturation is the purity, or how much white light is mixed in. Think of pink, it's just a heavily desaturated red. And intensity, that's simply the achromatic brightness, literally just sliding the brightness scale from totally dark to blindingly bright. So how do we bridge the machine's model with ours? Think of it like a giant geometric puzzle. You've got the rigid RGB color cube, which is perfect for computer memory. To translate that, it gets mathematically mapped onto the HSI model. The diagonal axis that runs right through the center of that RGB cube, from solid black to solid white, literally transforms into the vertical intensity axis of the HSI model. Then the hue and saturation are represented by circular and triangular planes perfectly perpendicular to that vertical intensity line. It is a brilliant piece of conceptual geometry. Which brings us to Section 4, converting RGB to HSI. We've visualized the geometry, but what does the actual translation bridge look like? How on earth does a computer take a bunch of raw voltage numbers for red, green, and blue and mathematically calculate human-like color perception? Well, it all comes down to some very precise trigonometry. To pull the hue out of an RGB pixel, the algorithm calculates an angle, let's call it theta, based on the relationship between the red, green, and blue values. Then it applies a critical little rule. If the blue value is less than or equal to the green, the hue is exactly that angle, theta. But If the blue value is greater than the green, the hue is 360 degrees minus theta. This clever bit of math ensures the hue wraps cleanly around that circular plane we talked about, letting computers seamlessly slide across the color wheel. And the best part? The math works in reverse too. So a computer can translate your HSI adjustments right back into the raw RGB values the screen needs.
Let's wrap things up with Section 5, Real-World Applications.
So why does all this mathematical gymnastics actually matter? Because teaching a machine to manipulate color unlocks some literal, real-world superpowers. By working with color data, or chrominance, algorithms can do amazing things. They can use false colors in medical imaging to isolate hidden anomalies in MRI scans. In computer vision, it allows a self-driving car to instantly detect the specific red of a stop sign. From tracking deforestation via satellite to breathing new life into century-old grayscale photos, color conversion is absolutely crucial. And we can't talk about applications without mentioning automated quality control. Imagine a factory assembly line churning out thousands of items an hour. A human eye is going to get tired. It's going to miss a slightly bruised apple or a subtly mistinted pill casing. But a machine? Using those perfectly calibrated color ranges we just talked about, a computer vision system can instantly and continuously isolate product defects. It pulls flawed items from the line with a level of tireless precision that our biology simply cannot match. I want to leave you with this thought. We started out by looking at the very narrow band of visible light our human biology can handle, and we saw how we've mapped that onto digital hardware. But as these processing models get smarter, and as sensors start pulling in data from way beyond our biological limits, what previously invisible aspects of our universe will we soon be able to clearly see? Thanks for hanging out with me for this explainer, and keep looking closely at the world around you.